Hi everybody, Dario Fresu here from fresuelectronics.com, and today we're going to take a look at this iMX8 processor, and we're going to review it in terms of EMC and signal integrity. Alright, so let's start this review. So the first thing that we're going to take a look at is actually the stack up of the board. And I want to do that because I want to have a clear understanding on how the fields are going to behave for this system on module. So I open here the stack up of the board, and I can see already. So first of all, we have a mixed signal layer in here. Then we have a power plane, then another power plane, then signals, and a mixed signal layer again. So first of all, I see already in here there can be some troubles because we have a mixed signal layer. So this means that we have a signals and power on the top. We have a power plane, so hopefully this is a return reference plane. But then we have another plane. So this, I hope this is either a power plane. And then in here we have a signal layer. So this signal layer in here, we can see that it has basically the reference of this. So maybe this one here is another return reference plane. And then this means that this signal layer would be probably coupling with this one here, with this power plane here. But then we have in layer 5 another signal layer, and we have a mixed signal layer in layer 6. So ideally in here you want to always think in terms of signal return reference plane, so always coupled. So never thinking in terms of one signal and then the other one another signal and then another signal. So we always want to choose the stack-up by pairing the signal layer with the return reference plane adjacent to it. And this, even if you think that you're going to place another signal layer instead of a return reference plane, you're not saving cost. This is only an appearance because you think you're saving cost by cutting down one layer, but then the cost that you save by not using this layer, you're going to see it when you try to do the EMC test or any other signal integrity test that you have for your board, because you're going to lose, first of all, the quality of the signals that you have, because we have to remember that the signal is composed by two potentials. One is the potential of the signal that you want to use, and the other one is the reference potential. So the signal is the voltage between these two potentials. And this is just a definition of it. So if we take one of these potentials away, we are only left with one potential. So there is no voltage difference anymore. So either you don't have a signal, or if the signal is there, then you have the signal established through the parasitics that find the return path for the current to close the loop. So always when choosing the stack-up, things in terms of pairs. So signal layer, return reference plane, they always go in pair. They never go just the signal layer. Because if you have only the one signal layer without having the return reference plane adjacent to it, then you're designing RF boards. You're not designing digital boards or mixed signal boards. So just be careful, because this one will get you in trouble in terms of electromagnetic compatibility. So this will produce some huge radiations, and either in this video or in another video, I'm going to show you why. So also looking at the stack-up in terms of manufacturing purposes, you always want to think about the stack-up being one side the mirror of the other. So if you choose a return reference plane on the second layer, then you want to choose also a return reference plane also on the fifth layer. And the same is in between. And this is because you want to have a certain symmetry of the board. So you want to have a board which is as symmetrical as possible, because otherwise you start to get into troubles. For example, in thermal behavior of the board, suppose that you have several signal layers in here, then the board, when it's going to heat up, is going to behave differently. And then you can also cause some warping of the board, and this can cause the component to start detaching from the board, from the soldering joints. You want to have the board as symmetrical as possible. So choose the stack-up first of all, by choosing the signal layer and the return reference plane always adjacent to it, and then try to make the Stackup as symmetrical as possible. Okay, we're going to take a look also at these layers more in detail to really understand which layers are in here. But then before we do that, I want to see what is the distance between the layer, because if we have in here, for example, the signal layer, then we want to have as close as possible the return reference plane. And here I see is 0.274 millimeters. Then in here also we have that on the third layer, we have another signal layer. We saw is a power plane, but I think that this one here is not really a power plane, but this one here is more actually a signal layer. So this is a signal layer with some copper pores in it. So this one, the third layer, this one here, is also at the same distance that the first signal is. So if we choose this type of Stackup, then we want to make sure that if this one is signal layer, this one should be the return reference plane. This one can be a digital signal layer, so this one can be only signals, but then is reference also this return reference plane. And then in here though, we want to have more distance, because otherwise this signal in here will try to reference to these signals in there. So what I will do in this Stackup is first of all reduce this distance here, and also reduce as much as possible this distance here, so that this signal couples to the return reference plane there, and also this signal couples to the return reference plane in there. And then in this way I can use this single return reference plane for two signals, because due to the skin depth of the signal in here, then I'm going to have the signals here which have the return reference current only on this portion of the plane, and the same will happen with this one here. Then I will have the signal which create a return reference current here only on this portion of the plane without interfering with the others. But this one I will definitely make it a little bit larger, so that this signal here does not interfere with this signal here. And the same I will do with the other three layers. So I will decrease this distance here, so that this signal layer will couple to this return reference plane. And the same I will do with this one. So I will reduce as much as possible this one, so that this bottom layer couples to this return reference plane. And of course, when I say that, I want to have in here a return reference plane, but also here a return reference plane. Now let's take a look on how the layers are really divided on the board. So we have in here the top layer, then we have return reference plane. This is connected to GND, so this should act as the return reference plane. Then we have on the third layer here, we have a mix, because we have some digital signal, but we have also some copper pores. Then we have again some digital signals with some copper pores. This is connected to some power polygon pores. And then again, we have some polygon pores in here. So we have some power planes, and we have in here digital signals with most of the components, and also some copper pores. So first of all, this is digital signal. So here, this is great because we have on the second layer a return reference plane. Now, what is not that nice in here, we're going to see later on, is this split there. But then this one here is digital signal. So I want to have this layer 3 coupling with this return reference plane on the second layer. And then I want to increase the distance between these two. Then let's see what is layer 4 is, again, digital signals with some planes. So this means that on layer 5 in here, I want to have another return reference plane like this one here. So let's see what we have. In here, we have some planes, but this is not good enough. And this actually can create some issues, and we're going to see later on when we analyze this plane. And here, we want to have, okay, these digital signals with the components. And so this one will have the reference plane in here with layer 5. So you can already see that in here, we can have some issues, but I'm going to explain you in a second. Okay, let's start from layer on the top. So layer on the top in here, first thing that I notice is that these copper pores can be a little bit dangerous because, okay, the designer here tried to use some stitching vias to connect the planes through the ground plane that we have on the second layer here. But the problem is that we have some kind of geometries that can create some antenna patterns. And I'm talking about things like this one here. You can see it has only a stitching vias there. And then we have this part which can act as an antenna. Then we have this part in here as well that can act as an antenna. And then also some manufacturing potential issues in here because this is quite thin. So most likely this is not going to be manufactured. So this one the same. And these parts, they still can create some antenna patterns in there. So I really don't want to have this one here because if you see, this is just an antenna pattern that we have because we have only one stitching via in there. And then we have all this part which is acting an antenna because in here is the only connection that I have to the return reference plane. So this one, I would like to get rid of this part in here for sure. And the same applies to other parts like that, like this one here. You see, it has only this stitching via, but then it has this point in here, which is acting as a potential antenna. So this can be a problem because between this point and this point in here, you're going to create some voltage drop. So this can be an issue, especially with common mode radiations. Why? Because in here you have this part which is connected to the return reference plane on the second layer, but the problem is that the impedance of this point is different than the impedance that you have at this point. So in here you're going to have some voltage drop. This voltage drop in here is noise, and this noise will couple to the return reference plane. And once you connect the cable to the ground, once you connect the cable to the ground plane, then this will act as an extension of the board and will create an antenna. And then what you're going to see is some radiated emissions due to the common mode currents that you create by having this voltage drop there. So really, you want to avoid these kind of patterns at all the cost. Because I think that in here the idea is that you want to keep the copper balance. But first of all, in this board, the copper balance, I don't think is going to be really an issue. And it's not going to create some warpage in here because we have quite some high density of traces in here. And also if you use the planes correctly, then this is not going to create many issues. So these patterns in there, you definitely want to get rid of them. Then let's skip forward a little bit. Then the other point that gets my eyes is this one here, which is we have on one side of the trace a certain trace width. So in here we have 0.08 millimeters, but in here then we have 0.1 millimeters. So ideally you want to keep the impedance of the traces always consistent. And you want to do that because you want to avoid that the signal, when it's propagating in the trace, reaches this point and sees this different impedance of the trace, and then it reflects back. And then it starts to create a reflection in here. So the impedance discontinuity is because the impedance is not anymore the same between this point and this point. You want to always have a controlled impedance. So if you think about it in terms of characteristic impedance, so the impedance that characterizes the line that you have in here, so think of this as a transmission line of the signal, then you want to have from the point that you start till the point that you end, and also the load, you want to always have the same impedance because otherwise you start to create reflections. So when the signal propagates like this, you don't want to have these points where in here, for instance, the impedance is 50 ohm and then in here is 60 ohms. So you have this 10 ohms difference between this point and this point. Now, I'm exaggerating to explain you the phenomena there, but you want to keep the impedance always constant. Because if you have in here, at this point, a certain instantaneous impedance, then if in here the instantaneous impedance changes, then you don't have any more a characteristic impedance, because you have two different impedances, and then you don't have one single impedance which characterizes the whole transmission line. So try to avoid these changes of impedance as much as you can. Beside this point, this is still okay. Depending on the signal that you have, you might have some reflection there. But other than that, I see that this is constant, that the differential pair in here are kept at a certain distance, so that there is some coupling in between, and you can avoid also some noise coupling to it, or better, if you have some noise, you can reject it later on once the signal reaches the load. And also what's nice is that you have quite some distance between the different pairs. So this is good because you're not going to have some crosstalk in this point. But I see that in here still, this is quite dense, so that's something that needs to be tested, but there is still some good distance in here. What it worries me a little bit more is that in here, instead, the distance is not as good as it was before. You can see in here, really, the distance is like one width of the signal traces. So definitely in here, I will get rid of this. First of all, even though in here we're using stitching vias, I will get rid of this portion of the layers, and I will increase in here the distance between the signal traces, especially if they are not differential pairs like in here, and you have actually a clock signal, which this one here, you have the clock signal which can easily couple to these traces adjacent to it. So you are going to have some crosstalk in there. So definitely I will increase the distance between these signal traces. Then we saw that we have, first of all, the issue of the stack up of the board. Then we have polygon force like this one here, but also others like this one there. Then the other point was in here, the trace impedance. So keeping the impedance that the signal sees along the way always constant. So not creating this kind of impedance walls. But then let's see, the other problem was in here, the crosstalk that we can have between these points, especially when you have some clock signals running through it, like this one here. Then you want to have as much distance as possible, so increasing the distance between these points. Then another issue that I saw, and this is quite common because I think this one is thought to be a little bit more advanced, but it's actually something basic that we have to start implementing in our layouts, and is the lack of return reference vias. So when I talk about return reference via, I talk about the vias connected to this plane in here, because the issue is that when the signal goes to transition from this layer to the other layer, which is actually the bottom layer in here, it has to transition to all these stack up in there. So it has to go from this layer and reach this part in there. So what is the issue in here? The issue is that, again, in here, the signal loses the reference for the signal. So I only have one potential in there. But the return current in here has to find other ways in order to follow the signal path and have this potential, this voltage between this return reference plane and the signal. So when the signal is trying to transition here, I always want to have a return via that allow us to, first of all, establish the return current. So the signal in here is always trying to establish the voltage for the signal. So this is the signal, which is established between, again, the two potential. One is the potential in here, which is our 0 volts potential, and our signal potential, suppose this is 3.3 volts. So in here, this is the signal. So trying to establish this voltage there between these 2 points. And this is consistent along the stack up. So when I'm transitioning from the top layer to the bottom layer, I want to have in here, some people call it stitching vias, but this is really return reference via, because it has to provide the path for the return current, but also the path for the reference of the signal. So what we can do in here is place right adjacent to this via here, we can place another via which is connected to the return reference plane. so which is connected to the plane in here. So if I place a via in here on this return reference plane, then the signal will always have this reference, first of all, for the voltage, to establish the voltage of the signal. So it has one potential which is given from this via connected to the return reference plane, but it also gives the path for the return current to flow back to the return reference plane. So each time that I'm transitioning layer, like in this case, here I want to have a via which is connected to the return reference plane, which gives this return path, but also the reference for the voltage. So this applies also for the other signal. So you can see that all the signals, when they're transitioning vias, they don't have in here some return reference via. Like this case, when this one crosses layer, it has this return reference via, so that's okay. But in here, you see all the signals crosses the stack up in here, and then this one will start to create some radiations. In here, you're gonna have radiation on the side, radiation on the other side, and then this one will spread throughout the whole plane in here, throughout the whole plane of the board, and these will cause some resonances and then emissions. So this was the next point. So no transitioning vias when crossing the layers. The rest, it looks okay. What I would have used in here, maybe some copper pores in here to connect these points, rather than having these small loops that we are creating, these empty squares. And then one of the points maybe will be to check what the time match in here. So if we time match these signals that we have, and also I would have changed probably the way this time matching is done. So the way this time matching is done in here. Anyways, this one should be okay, but also this point in there. Then let's jump to layer 2. So layer 2, we said that this one was almost good. Now, why am I saying this is almost good? Because in here, I can see that there is some sort of a split between the two planes. So we have a plane, which is this plane here, and this is actually connected to the ground. But then we have also this plane here, which is still connected to the ground. But I see that between these 2 points, there is this gap. So there is a gap between one polygon and the other one. So this is 2 polygons in here. And you can see that this one, first of all, this is not good because we have some signals on the top that cross these splits. So when we're crossing the split, what happens is that the signal comes to this point, and then in here, the signal is lost because it doesn't have anymore the reference potential underneath, and it doesn't have the path for the return current when it's crossing this point. So then the fields will spread throughout to this cavity. And the cavity, what is the cavity? The cavity is this break that we have between the planes. So the plane in here and the plane in here, and the cavity is this one there. So the cavity is all this void in between the 2 planes. And then what happens is that the signal comes to this point, but when it reaches this void in there, then the signal starts to spread in both directions. So the fields of the signal start to spread in this direction to find the return reference path. So to find also the place for the return current to close the loop and return back to the source. So these will create some issues, first of all, in terms of signal integrity, because when the fields start to spread in this cavity, will also couple to all the signal in here. So the signal, the signal, the signal, the signal, the signal, and this is an issue, because this is going to create some sort of crosstalk. But then also because this one can extend throughout the whole part of the cavity, so throughout all the split, and it will create a certain resonant frequency that will radiate out of the board. And you can see that this is basically has created some sort of loop in this plane. So you have this plane in here. So when the fields are injected in this cavity, then you have a resonant cavity that is going to resonate a certain frequency, and this you're going to see it when you measure it with the EMC. So now the question is how much? This is another question because you will have to measure it. But for sure, this is not going to be an easy issue to deal with. you see all these signals going through the splits in the planes. So this is definitely not good. So then let's go back to layer 2. The other issue that I see is that we have here these large gaps, which can be avoided by simply increasing the distance between these two vias, between this via here and this via there. So you can increase the distance here between these two so that this copper fill can fill up this area there so that the current also can flow through this point. Because otherwise, if you have some signal on the top, like we have, now in this point is not an issue, but on this point in here, it can be already an issue because you're just creating in here this void, this big hole where the current cannot flow and then the current has to go in other directions. Just by simply increasing this distance, so increasing the distance between the vias, you can still have some copper fill in there, some copper fill where the return current can flow. And you want to do this in here, then the same, you want to do it there, the same you want to do it here, and in all the other places like that. So this one, I will definitely improve it a little bit, just by spacing the vias a little bit more, so that you have this kind of situation where the copper pool can fill these parts. The other point that I thought it was good in here is this stitching vias at the edge. So this is sort of creating a Faraday cage for the board. So you have in here like a Faraday cage for the board throughout the whole perimeter of the board. Now the question is, where are these stitching vias connected? Because you can also create some other issues if the stitching vias are not connected on the other side of the Stackup. Because this point, if you have some high switching signals inside the board, what can happen is that these stitching vias that you're using, if they're only connected to one side of the board, so if they're only connected to one plane, what can happen is that these vias, they become a stub. So they become some parts of the plane which can resonate at certain frequencies, and then these can create issues because they can behave like an antenna. Now let's take a look at layer 3. Okay, so this is quite packed. So ideally in here, you want to use, first of all, I would have again removed all these polygon pores because actually in here they're taking space for the layout. You see that in here the layout is quite dense. So there is quite some vicinity between different traces. And this is going to create a crosstalk, like we said, because the fields of the signal in here, they can couple to the signal there. And this is going to create a noise in this net, in this trace. And then you're going to have other signal integrity issues or even EMC issues if this then connects to some cables. So definitely in here, I would have removed all these ground planes, all these ground copper pores, and I would have used the space a little bit better to increase the distance between all these traces that we have. Especially if you can see you have some quite fast switching signals, so you really want to take care of those. I see in some point the designer use these stitching vias to connect these polygon pores so that they don't behave like antennas, but you really want to be careful because this one it's okay, but then this I don't think is okay anymore, this part as well. Okay, so now this is, we set the copper pores, then the traces too close to each other, so this is again some crosstalk, especially in here. You can see that we are very close, first of all, to the edge, also to the other traces. So here I would have increased the distance between these traces there. Then let's go to layer 4. Layer 4, the same. We have some copper pores, which we can get rid of and use actually this space a little bit better. And the thing is that in here we are also connected. This is VCC DRAM. So this we are supplying the DRAM with this plane. But this, remember, this is layer 4. So if you use in here some planes, then just use the planes. But in here, then you want to have a return reference plane. And in here, instead, we don't have a return reference plane. So we are trying to use power on the layer 4 but then the next ground is on layer 2. So when you think in terms of energy, how the energy is delivered to the DRAM in this case, because we were saying that this plane in there is connected to the DRAM. So we are connected to the DRAM here. How are we going to provide the DRAM with the energy that it requires if we have the power plane on this layer, but then the ground layer is here? So the return reference plane is on this layer. You can see that in here you have something in between, which is not good, because this layer now is in between these two power layers. But then also this layer in here is not going to deliver the energy to the DRAM because it has the return reference plane so far from it, because you see there is the distance between the dielectric between these two layers, plus there is the layer, plus there is again the distance between this layer and this layer. So there is these two dielectric that it has to cross. So we have to remember that the fields are not in the copper here. There is no electric field. The electric field is established between the return reference plane and this power plane there. So between this plane and the return reference plane, there is the energy and there are the fields. So choosing a stack-up like that, you're really going to create some issues for you in terms of electromagnetic compatibility, because all it is electromagnetic compatibility is the measurements of the fields. So how the electric and the magnetic fields are behaving from your circuits and on your circuit. And choosing a stack-up like that is not the best choice. When choosing the stack-up, I want to emphasize it again. Always choose signal return reference plane, and even when you choose power return reference plane, always adjacent to it. So they always go in couple, they never go single, especially if you have digital signals. Okay, I understand you want to make the board cheaper, but then you spend 20-40K in doing again the EMC test, plus you have to change the layout to make it pass EMC. And I know for a fact that this board is actually sold as an industrial module. So I don't know if this was done by choice or because the electromagnetic compatibility test couldn't be passed for the domestic limits. And this can be one of the reasons why, because in my opinion, this stack-up is not chosen right. Okay, let's proceed with layer 5 is power. So like I said, this one should have been instead a return reference plane, so should have been like this one here, of course without the split that we saw, without this split and this split. So this should have been a full return reference plane. So no splits, no cuts. You can see that this one is power planes, and basically is chunks of power plane that have splits. And really the issue in here is that we have the other bottom layer then, which crosses all the splits. So you can see these signals are crossing the splits, these signals are crossing the splits. So this is definitely going to create, so first of all, some differential mode radiations, but also some common mode radiations, because the return current will have to flow through all these large planes, and then it has to connect at some point to the ground plane, so to the return reference plane. And here, now I'm going to touch another controversial topic, which is that when people tell you that you can still use the power plane as a return reference plane for the signals. So this can be done, but to a certain point. And why? Because, first of all, the return reference plane is because of the return current, but also for the reference. So yes, the power plane can be used for the return current, but then you have to be careful, because at some point, still you want to have either with the decoupling capacitors, which are going to compensate for the low frequency part, because they're not going to be useful anymore when you have high frequencies because of the impedance of the capacitor. But also you have to think that the power plane is electrically disconnected from the return reference plane. So from the ground, from what you use as a ground, this plane and this plane, they're electrically disconnected because one is power, the other one is ground. How does the current flow back to the ground plane if these two are electrically disconnected? It does so by the coupling capacitors at low frequency though, so only the low frequency parts return to the coupling capacitor. And of course, the coupling capacitor also, they have to be established properly throughout the board and also in the pinouts of the microcontroller or whatever you are trying to decouple. But then the high frequency part is going to use the distance between the layer, which is the impedance between the two planes. So between the plane, like we said before, is going to cross this plane, so this plane in here, to reach this point in there. So the return current loop for the signal on the bottom will be established through the power plane, but then it has to cross all these planes and reach the ground plane in there in order to close the loop of the current. So the problem is when it does the crossing in there. So how does it do the crossing if in here these two planes, one is grounded and the other one is power? There is the impedance between. This impedance is going to create a voltage drop because the current flows through this impedance, and then you can see already that you have a voltage drop. This voltage drop is noise. This is going to be detected when you do the EMC test. But also, how does the return current if these two planes are electrically disconnected from each other because this is ground and this is power? How does the current crosses from this point to this point? It does so by using the displacement current. But when you use the displacement current, then first of all, you don't know where the displacement current is going to take place in the layout, because the displacement current is going to try to find the path of least impedance. And then when it finds the path of least impedance, you don't know what is the impedance in between this point in here and this point in there. So between the power plane and the ground plane. And then you don't know what's the noise that you're going to have, because if you have an impedance between the power layer and the ground layer, then you're going to have some voltage drop when the current flows through it. And this voltage noise is going to spread throughout the board because it's spread throughout the planes, and it's going to create some issues. So don't use the power plane as a return reference plane. I wouldn't use it because it's too risky. It's going to create some issues at some point. So always use the return reference plane, what you're calling here ground. Use it every time you have a signal layer, you want to have it adjacent to it. Okay, so we saw that this plane can create some issues because we have this crossing. So we have signal crossing the splits, and this is big troubles for us, especially these high-speed signals there, big troubles for us. Then again, in here we have some signals very close to each other because we have these copper pores. Again, we want to use some distance in there. Then we have these antenna patterns. I saw some antenna patterns in here, like this point in there. So you see in here we have this one, this kind of geometry there, and you don't want to have for sure for manufacturing purposes, first of all, but also for EMC purposes, because these are just antenna patterns. And you can see that this is throughout the whole connector. So you're really creating this very nice antenna pattern in here where you have high-speed signals. And it doesn't matter that this is connected to the ground. It doesn't matter at all because this point in here has a certain impedance. Between this point and this point, you're going to have a voltage drop when the signal couples to it. And this is going to create some radiation at some point. Then I see in here we have a split. So we have a split in here. This is another impedance discontinuity. So the signal starts from there and then splits in these two directions. So it has an impedance at a point and impedance at another point. This is going to create some sort of reflection. You always have to think in terms of routing point-to-point connections. And then also here again, it has an impedance discontinuity because the signal reaches this point and then the impedance of this point changes from the impedance of this point. And then this is going to create some sort of reflection there. because in here, in the pad, then you have the impedance of the pin, and hopefully you have it matched as well. Again, the same problem with not transitioning vias, even especially for this pair. In here we have the PCIe, so PCIe connection. So I will really be careful with this connection there. You want to have in here the return reference vias, so the stitching vias. You want to have them in there, especially you have a clock running close to these traces, multiple clocks in here. I will then route it like that. Increase this distance between the traces. These traces are far too close to each other, very close to each other. This is crosstalk 100%, because you have signals running like that, and then this one will couple there, and then will start to propagate on this trace. So you want to increase this distance here. Okay, so I think that we saw most of the issues that are the biggest issues. Then, of course, if we go more in detail, then we can see if really the controlled impedance of the traces has been respected or not. But I think I have my doubts that the controlled impedance of the traces is respected in this case. So overall, I think that this, by choosing a better stackup, can be improved quite quickly, simply by choosing a better stackup, getting rid of all the polygon pores, and using also the space of the board a little bit better. For example, by cutting this, taking out the polygon pore in there, and just using the space to create better connections. Okay, so if you also need help in terms of EMC and signal integrity, you are going to find the links in the description below, or you can just simply go to fresuelectronics.com and you're going to find a way to reach out to me and to ask for some support with your project. Thanks for watching. Bye bye.